Okay, here we are at the next section, 13.3, and the topic of the day is supposed to be arc lengths in space, but I can't fit arc lengths in space in the amount of text I have allowed here, so arc length in 3D is what it is. All right, so once again, this is a pretty easy step, I think. I mean, you're always hesitant to say that. But it's a pretty straightforward step from arc length and parametric. Arc lengths in 3D space. Okay. So let's just quick review arc length. Okay. But I'm going to sketch it as best I can in 3D. So here we have our 3 dimensions, and then I'm going to draw kind of a little path to get to where I'm going. Well, let's make this X, Y, and Z. And so if I draw this path, I'm going to go a certain direction in the X, and then a certain direction in the Y, and then a certain direction in the Z. And then so I've got now some vector or a shortcut, a straight line in which I'm interested in the length. And if we look at this thing, we know that the length of it, s squared, equals x squared plus y squared plus z squared, right? That's just kind of like the 3D version of the Pythagorean theorem. Well, we can say that if I took out of a 3D curve and I'm just taking a little bitty chunk of that, I could write that ds squared equals dx squared plus dy squared plus dz squared, right? Well, what I'm going to do is factor out a dt squared out of this thing, and that seems like a little silly, but I'm going to do it anyway. I'm going to ds squared, and I'm going to take out a dt squared of this thing, which leaves dx over dt squared plus dy over dt squared plus dz over dt squared. And if I just want the differential arc length, I can take the square root of this whole thing. And so that gives me that ds equals the integral of, oh, not the integral yet. This just becomes the square root of dx dt squared plus dy dt squared plus dz dt squared, and then this dt I'm going to move over here, and so the square root of that is just dt. And now I can integrate both sides, right? And then I'm left with the arc length equals the integral from some time a to some time b over the square root of all this stuff squared dt. Okay, so our arc length formula, or the length of a curve, is pretty straightforward, but it's important to recognize this. Now, you might also recognize, remember, or recognize that velocity, the velocity vector, right, as we defined it before, which is dr dt equals, well, something that looks very similar to this. dx dy, or that's not right. In parametrics, it's dx dt plus dy dt plus dz dt, So this is starting to look like this if we square the individual components and then take the square root. Well, that's a lot like taking the magnitude. So I know that the magnitude of my velocity vector equals this whole thing. Dx dt squared plus dy dt squared plus dz dt squared. So that means that my arc length, or length of curve, the length of a curve is the integral from a to b of the magnitude of the velocity vector, dt. So if we know the velocity vector, we can get the magnitude of the velocity vector, we can just integrate that. And so that becomes a much easier way to go through and get the length of this arc. Okay, so the next thing I'd like to do is an example similar to the glider we did the other day. So start this on a new page here. So we're going to do a simplified glider example. And why do we use these gliders? Because there's not a lot of things that, helixes that happen in the real world that are moving, and a glider is a good one. So this glider, the position vector, is going to turn out to be just simply cosine ti plus sine of tj plus a little easier one here, tk. That's supposed to be a hat. All right. So now what does this do? Cos ti sine tj, right? That gives us a circle in the xy plane, and then this tk just means it's gradually moving up. So the challenge now is to find the total distance flown from t equals 0 to t equals, wow, what's an interesting value of t? How about 2 pi, right? This is a very contrived academic problem, so we'll go from 0 to 2 pi. Now we know that L equals, what does it equal again? The integral of the magnitude of the velocity vector dt, right? And I know that v equals dr dt, which in this case equals derivative of cosine is negative sine of t I, and then derivative of sine is cosine plus cosine of tj, and the derivative of t is just 1. Okay, and there's some interesting stuff going on in the background right now, but I'm just going to stay focused here. It's pretty funny, actually. If I'll tell you about it in class. Oh, maybe I'll have to pause for a second here. All right, so we're not actually interested in the velocity, we're interested in the magnitude of the velocity. So the magnitude is the square root of the individual components squared. So square root of sine t squared negative sine t squared, that's important to do this, plus cosine t squared plus 1 squared. Well, sine squared plus cosine squared is 1, and then so 1 squared is also 1, so the magnitude of our velocity just becomes the square root of 2. All right, so now to get the arc length, we integrate this from 0 to 2 pi of the square root of 2, so this is L equals the integral of root 2 pi, which equals root 2 times t, right? It's a very easy integral from 0 to 2 pi And this equals just root 2 times 2 pi. So let's look at this. Yeah, our flight path in the xy plane is a circle, right? A counterclockwise circle starting at the right side. And the radius of this, what is the radius? Because there's no leading coefficient here, the radius is 1. So the circumference is 2 pi. But we're climbing, so the 2 pi gets converted to, let me undo that there. Okay, it gets increased kind of by like a hypotenuse factor, which makes it square root of 2. All right, so it's a square root of 2 times 2 pi. But what if, I didn't want to go through this every time. What if I just wanted flight distance directly as a function of t, right? So I don't want to have to go through and do all this work every time. So let's take a look. I'm going to say that the length of this flight as a function of t equals the integral, but I'm going to say from 0, but instead of fixing it at 2 pi or pi over 2 or whatever, I'm just going to go up to t. Right, I'm going to go to t. So I'm using a variable in my limits of integration. While this remains mostly the same, this is still the velocity, but since I've already used t here, I can't use t again because that'll get confusing what t's are what. So I put in another variable here, tau, and then I make this d tau, right? And so in this case, tau, I'll do this as a little sidebar here. This is called, tau is a dummy variable. Or a variable of integration. So oftentimes, if t is kind of the variable that we were interested in, but we can't use t, we'll change it to tau. Another one you'll see is x. Well, if we can't use x, what's the Greek similar letter to x is c, right? This is xc, like that. And so these are variables of integration. If we've already used the variable where we want. Okay, anyway, if we do this thing now, this becomes, let me go back to black here. The velocity vector is still the cosine, so this is still the square root of negative sine tau squared plus cosine tau squared plus 1. So that stuff all stays the same. D tau, I gotta integrate this. And then put the d tau here. And so that equals, do the same thing. This sine squared plus cosine squared is 1, so this becomes the integral of root 2 d tau from 0 to t. That's 0. And then when I do this integral, that equals root 2 tau from 0 to t, which equals root 2 t. Okay. Well, really, what does this look like? This looks like speed times time, which should be no surprise. We knew that already. So in general, we can say that the arc length as a function of time equals the integral from 0 to t, or from, well, we can even say it's some initial position, t0 to t, of the magnitude of the velocity function of tau, that needs to be a tau, because I've already used t's, d tau. And so if I take the derivative of both sides of these, so ds dt, right, this is the length and the time derivative of length, ds dt equals the derivative of this integral. Well, the fundamental theorem of calculus says that that's just the integrand. And now I haven't used t anymore, so I can go back to t. So what does this say? That speed equals the magnitude of velocity. And again, so we've backed into this another way, that speed, ds dt, I'm not concerned about direction, is just the magnitude of velocity. All right. So as long as we're talking about velocity and speed, I'd like to address one more little issue here. What do we get if we divide velocity by speed? Right. Well, first of all, what does that look like? That looks like the velocity vector divided by the magnitude of the velocity. Well, we know from previous work that this gives us a unit vector. Looks like that. We call it v hat. But we give that a special name because what this really gives us is the direction, a unit vector that's in the direction of motion. So if that's at some point on the trajectory, on the path of this particle, what does that give us? It gives us a tangent. It gives us a unit vector tangent to the path. So that gives us what we call this thing t, which is called the unit tangent vector. Unit tangent vector. Okay. And so another way to think about this, if we do a little algebra here, we could say that the velocity equals some magnitude of velocity times this v hat. So the vector is a magnitude and a direction. Of the vector velocity is the magnitude and the direction equals the magnitude times the direction. Okay, so this tangent unit vector is a direction, it's a unit vector, and it's in the direction of travel. So if we go back to this original glider problem, the original glider from, where was that, 13.2, and I believe that the position vector came out to be something like 3 cosine of ti plus 3 sine of tj, and then had this kind of funny thing here, t squared k. And then so now if I want to get the velocity of that thing, it's just the derivative of this, so that becomes negative 3 sine of ti, and that becomes positive 3 cosine of tj, and what does this become? 2t k, like that. Now the magnitude of this thing, so if we square things a little bit, then that becomes the magnitude equals, well, if we square this, it becomes 9 sine squared of t, 9 sine squared of t, plus 9 cosine squared of t, plus 4t squared. And since it's the magnitude, of course, we have to square all the components and then take the square root of that. Well, we can see that sine squared plus cosine squared equals 1, so we can factor out that 9, and that just becomes a 9 plus 4t squared. So I go over here and I will write the magnitude, or the speed, equals root 9 plus 4t squared. So that means my tangent unit vector for this, so this is the direction only at any point along the path as a function of t, is negative 3 sine of t over this magnitude, which is 9 plus 4t squared, that's I, plus 3 cosine t over the same thing, 9 plus 4t squared, plus, or that's j, and then finally the k term is just the 2t over the square root times k, and 9 plus 4t squared. Alright? So this gives me the tangent normal, or the tangent unit vector. This gives me the direction of travel only, just the direction. And that becomes a pretty powerful tool, especially in the next couple sections. So you might ask, or I will ask, why didn't I use, why not the simplified version? You know, why didn't I use that? Or just going, if it's just, how about a glider flying in a circle, and I said that v equals, say, cosine ti plus sine tj, right? Why would I not use this one? Well, let's take a look at the magnitude of this one. The magnitude of this particular one equals cosine squared t plus sine squared t. Well, that just equals 1, right? So for the simple circle of radius 1, so i.e. if I'm you know, kind of tracking my velocity around the unit circle, which is what this describes, you know, the tangent vector, the velocity vector, is the unit tangent vector. They're the same thing. So that is just why I had to revert back to this old, the previous glider example. Okay, that is it for this section. The homework is posted, and I will see you in class. Thanks.